Okay, this is it, y'all. This is the last lesson that I'll teach you this year. But keep in mind, if you ever go back and watch this later, or somebody not in our classroom, that this lesson is being taught after 12.4, which is the lesson on how to calculate derivatives, especially with the shortcut way. So even though we're going to talk more about the definition, just keep that in mind. So as I mentioned before, one of the important things that we want to know is how to find the slope of a function at one instant or point on its graph. So when you look at these, if I wanted to know what the slope was at that point, well, if I started up at this point and I found the slope of that line, but then I drag that point down a little bit and get the slope of that line and drag it closer and closer to this point, then I will get closer and closer to the slope of what we call as the tangent, which happens to be also, as we mentioned yesterday, the instantaneous rate of change. So the best of these linear approximations is called the tangent line, and the slope of that represents the rate of change of the slope of the curve at that instant, hence the instantaneous rate of change. Okay, so our instantaneous rate of change of f of x at any point of the slope is the slope m of the tangent line. So the slope of the tangent line is equal to the instantaneous rate of change. Well, as you know, that is what we discussed yesterday as the derivative. So look at what you got to be able to do, but we're going to be doing it this short way because we already learned how to calculate them. So this first example, find the slope of the line tangent to the graph at the given point. So in these first examples, we are doing it at a specific point. But regardless, when you find the slope of the tangent, we're going to take the derivative. So the first thing I'm going to do is take the derivative of y equals x squared. That's equal to my slope. To take the derivative, I move the exponent down front, and then I lower the exponent by 1. So I'm going to have 2x. And in this case, they want me to find it at the point 39. Well, I'm only interested in the 3 because that's the x value. So I'm going to plug in x equal to 3. And when you simplify that, you get m equals 6. So the slope of the tangent line at that point is 6. Look at 1b. Y equals x squared plus 4. So if I'm looking for the slope of the tangent, I find the derivative of it because the slope is equal to the derivative. So I look at the first term, move the exponent in front, reduce the exponent by 1. If it doesn't have an x in it, then it's 0 and it goes away. And now I'm looking for it at the point negative 2, 8. I'm only interested in that negative 2. So I'm going to plug that in. 2 times negative 2 is negative 4. Okay, so that was the slope of a graph at a point. If they want the slope of a graph at any point, then I just don't have to plug in, and all I have to do is find the derivative. So on this first one, well, that was smooth. Let's go back here. So y equals, again, we've been doing that. So move the 2 down front and reduce the exponent by 1, and then negative 4x. The exponent is 1. 1 times negative 4 is negative 4. And when you reduce it by 1, then it goes away. All right. Then we have y equals x cubed. So that slope is move my exponent down front. And I say move it down front, y'all, but I'm multiplying it by what's there. And what's there is a 1. So move it down front and then reduce the exponent by 1. So it's going to become m equals 3x squared. Or the slope of the tangent line at any point is equal to 3x squared, and you plug in whatever x you want. Okay, average velocity. Okay, the key word here is average, y'all. Average velocity can be calculated using the same approach used for calculating average speed. Okay, now average, that's basically the same thing as our average rate of change. But it does look, and so it is the change in the distance over the change in time. And the change in the distance was what we get when we subtract our y values, and time is what we get when we subtract our x values. So that should look very familiar to you in that it is the slope formula. Okay, so Average velocity. While the balloon is propelled straight up using a launcher, the height of the balloon in feet t seconds after it is launched can be defined by this function. What was the balloon's average velocity between t equal to 1 and 2? So you've got to remember that keyword is average velocity. Average velocity is like the average rate of change, which is like my slope. So I have to go find the y values that correspond to these x values. So I'm going to take the 1 and plug it in here, and the 2 and plug it in here. So when I do, then I'm going to find out that d of 1 is equal to 54, and d of 2 is equal to 71. So now I'm going to go use the formula that we just showed up there, and my average velocity. Now keep in mind, you should do the bottom first because you need to keep it in that order. So you go from the one further in time, so 2 minus 1, and you've got to get the corresponding y values. So what goes with the 2 is 71, and what goes with the 1 is 54. And when you subtract 71 and 54, you get 17 over 1. So the key is my average velocity. This is the difference between these problems and asking for slope, y'all. You got to have a label. So you can look back at the problem and see that it gives you information of feet per seconds. So that is the label that goes on my problem. Okay, next we have the instantaneous, and this is what I talked to you about yesterday and at the beginning. Okay, our instantaneous rate of change is if you think about calculating those slopes such that the difference between them gets to 0. Okay, this is our definition of the derivative. Okay, so the instantaneous velocity is equal to the derivative of the function that you were given. Okay, so here is a word problem. A window washer accidentally drops his lunch off the scaffold 1,400 feet above ground. The position of lunch in relation to the ground is given with this formula, where time t is given in seconds and the position of the lunch is given in feet. Find the instantaneous velocity, v of t, of the lunch at 7 seconds. Okay, so if we are finding instantaneous velocity, then that means we got to go find the derivative. So, and that means that the derivative of our function is equal, the velocity is equal to the derivative of our function. So I'm going to go calculate the derivative of that. 1,400 goes away. 2 times negative 16 is going to give me negative 32. And then I reduce the exponent by 1, leaving me with just t. Okay, so that's the formula to find it at any point. They asked us to find it when at 7 seconds. So I'm going to go take that and I'm going to plug in 7. And negative 32 times 7 is negative 224. Instantaneous velocity, I need a label. Okay, and they told us in the problem that it was feet per second. So we're going to have feet per second. Okay, last problem. The distance in feet of a water rocket from the ground after t seconds is given by this formula. Find the expression for the instantaneous velocity of the rocket at any time. Okay, so again, instantaneous velocity anytime means I'm not going to be plugging in a number for t. I just have to go find the derivative of that function. The velocity equals the derivative of whatever the function is that they've given you. So when I do that, I'm going to have v of t equals, all right, I'm looking at 90t, okay, and the exponent is 1 times 90 is 90, and the t is going to go away because it's t to the 0. Minus 16t squared, 2 times minus 16 is negative 32. Reduce my exponent by 1, leaving me with t, and that is all you have. And we're done. If you have any questions, please don't hesitate to contact me or come see me. Hope y'all have a great day. Thank you so much for watching.